Hypothesis testing is our mathematical way of understanding whether a statistic, so some calculations done on a sample from a population, is significant. It has some sort of impact in the real world. It might force us to change our mind about something we previously understood. And whenever you're doing a hypothesis testing question, regardless of whether it's with the binomial or later on with the normal, there are 4 steps that you need to go through, and they form the kind of backbone of your response to these problems. So the first step is to set up your hypothesis. And this is your model. This is you interpreting what the examiner has asked you about, I guess, and writing out a mathematical scenario that you can then solve to find an answer to the question. Part of that is the significance, and that's the second thing you've got to set up in your problem. And that we're going to come on and talk to just a little bit later on. The third thing is then that you test a sample, and we're going to test it under the situation that we've identified in 1 and 2. And then lastly, we have to conclude. So we have to make some sort of judgment or decision within the context of the question as to whether or not our hypothesis is true or not. So here's a little scenario. Now, it's likely that you wouldn't get something like this in the exam. You'll need to check out later videos for the exam style questions. But I found this sort of situation really helpful for understanding sort of what each part of a hypothesis test is about. So say I want to know whether maths students are actually learning anything in lessons. So I give a 20 question test to everyone, and it's a multiple choice test, and each question has 4 options. So I would expect then that a monkey or a student who isn't learning could correctly guess the answer 1 in 4. Because you just go for A every time, or A, B, C, D, A, B, C, D, A, B, C, D, whatever. You pick a random way of selecting it, and we would expect that you could, by luck, get a quarter right. So that would end up being 5 answers, maybe, perhaps. We would sort of expect. This is actually the expected value as well. But that's it. You know, if you were just guessing 1 in 4, it's likely that you could get 5 right. But I want to know, at what point can I say, yes, students are learning? So what I'm going to do is I'm going to suggest that if they're not learning, the probability of them getting a question correct is as good as a lucky guess. They may as well be a monkey, just randomly hitting buttons or writing the letters A, B, C, D. So that's my, what we call a null hypothesis. Nothing changes. You're all monkeys. So we are, spell hypothesis, hypothesis, there we go. Nothing changes. I can't say on accepting the null hypothesis that you're any better than monkeys, that you are learning anything. If, however, you are learning something, if the maths students are learning something, I could reasonably suggest that the probability would be greater than making a random guess. That you're able to apply some sort of logic or knowledge of skill or ability to problem solve and increase your chances of getting questions correct from just lucky guessing. This is called the alternative hypothesis. If I can accept the alternative hypothesis, that means I can change my mind. So here I want to know whether or not you're learning anything, and at the moment I don't think you are necessarily, potentially. If it comes out that actually we could accept a probability higher than 0.25, then that's exactly what I will do. So I need to test whether the results that I get are significant. You know, so if I give you tests, how do I know that you're actually learning? How do I know that the results that I get from those aren't just down to chance, they're down to the fact that you've learned something? This is what hypothesis testing is trying to do. What we now need to do is decide on some significance. So how significant do I want my data to be? How certain do I want to be that I've actually calculated something that forces a change of mind than just is within the sort of statistical possibility? So you tend to see hypothesis tests at 10% significance 5% significance, 1% significance, and sometimes, if you're lucky, you can get something at 0.1%. So obviously, the lower this is going down, the more certain we are. So this is sort of increased significance or certainty. Within here, we're saying that we are, this is the probability at which point we would say if it's lower than this, there is something significant going on here. There is something statistically different to what I'd previously imagined. If it's higher than the value that I pick for my significance, I'm saying no, it's actually statistically likely that it's going to happen. It could just happen by fluke on the numbers. The monkeys could just hit the right numbers and come out with a score of whatever. So then we're getting more and more accurate then. And obviously, depending on what your context is, they'll be more and more appropriate. So for medical trials where people's lives are in danger, you're going to want to be pretty sure that what you suggest, whether it's a new drug or a new treatment, is not just left down to chance, but you know it's had an impact. So here we are then. So I've kept my null hypothesis as 0.25. It's as good as chance. My alternative hypothesis is that your values are high enough for me to suggest that actually you are better than chance, that there is something, some sort of learning that's gone on. And I'm going to test at a 5% significance because I think your learning's important. But you'll nearly always be told exactly which significance to test at. Okay, so here are some situations then. In one class, the average mark was 8. Right. Okay, so let's take x to be the random variable of questions answered correctly in test. Don't forget, you always need to define your variable, and we're saying that x follows a binomial that out of 20 questions, probability of getting any one of them correct is 0.25 when that probability is based on chance. Now, what am I asking? I'm asking about getting 8. But any one individual probability is really small because it's saying 8 and no other values. And nearly always that will lie under 5%. So that's not a particularly strong statement. That's really not disproving or proving anything. What I want to do is have a really strong statement. So I want to say something like probability of getting 8 or more. So let's have a look at the probability of getting 8 or more. Well, that is 1 minus the probability of x less than or equal to 7. And if you use your calculator, you can work that out to be 0.108. So there is a 10% chance of getting 8 or more. Well, that is greater than 5%. So I can't say that this class, there we go, 0.05. I can't say that this class has learned anything. That is still very statistically significant. It is quite possible that the monkeys hitting the desk or a computer or scratching out the letters A, B, C, D have a 10 or almost 11% chance of getting 8 or more correct. 11%. That's nowhere near the 5% significance that I wanted before. So I'm going to have to accept that this group are full of monkeys and I can't change my probability. In another class, the average mark is 10. Okay, well, let's have a look at that one then. So we'll still keep same x. Let's just say as above. So it's the probability of getting questions correct. And I've still got the same binomial, still the same problem, and I'm still for now assuming that you may as well be guessing. There's a 1 in 4 chance of getting a question correct. But this time I'm asking about 10. Now again, equal to 10 would be a very, very small probability because it's saying 10 and absolutely nothing else. it's far stronger to ask about what's happening if I go greater than or equal to 10, so 10 or more answers. Now if that alone is, combined is less than 5%, then that's quite a strong statement to have made. Okay, so that is 1 minus the probability of x less than or equal to 9, and that comes out as 0.0138. Oh, here we go, 0.01386. Okay, so there is a 1% chance that if you are a monkey bashing keys or scratching out the letters A to D, a 1% chance that you could get 10 or more. Well, that sounds significant to me. That's under 5%. That's under our 5% threshold. And so we can say now, accept H1. I can actually say for this group, yeah, I think learning's gone on, because the chances of this happening by luck, I guess, by chance, is 1%, and that's not a big number. That's not a big probability. So I can accept H1. Now the last thing I've got to do in both of these cases is interpret this in the context of the question. So in my first class, I need to write exactly what I sort of said. They're all monkeys. I'm not going to write that, but it's no significance or no significant evidence to suggest. Okay, there we go. Learning. What's my pen doing today? Learning has occurred. And in this case, the second case, there is evidence to suggest that learning has occurred. So hopefully that's given you a little bit of a foundation to what a hypothesis test looks like and the reasons why we might go about performing one. I would definitely suggest that this video needs watching a couple of times. It's a little overwhelming, an idea, and it will eventually sink into your brain. But just to say that each one of these stages, because you're communicating an argument, if you like, can't be missed out. You do have to set up your hypothesis. There are marks available for it. You have to acknowledge your significance. You have to set up a full sample and whatever probability test you're doing on it. So that's defining your binomial or defining your normal later down the line. And you do have to conclude within the context of the question. In the next video, we're going to look at some proper exam style questions and look at setting up these so that they communicate your ideas as clearly as possible and gain you all the marks.